I'm going to be speaking about QCD, the power and the glory, or the glory and the power means the same thing. But I'll be speaking about glory first, so I changed the title slightly here. What is QCD? Well, there are four fundamental forces of nature as we understand things today: gravitation and electromagnetism, which have had profound understanding already in the 19th century and have effects on macroscopic scales. So they are the material, the forces that one learns about in engineering courses, for instance. But in the course of the 20th century, physicists found that those two forces were not enough to explain what goes on inside atoms, and they invented two new forces, which was found that one needed two quite different new forces to explain everything that was observed. And one of them, they don't have very imaginative names. They're called the weak interaction and the strong interaction. The weak interaction has to do with decays of particles, and it's relatively weak. Anyway, I'm not going to talk about it. Today's subject will be the strong interaction. A good way to introduce the strong interaction is as the latest and probably final development in our understanding of how matter is made up. So atoms, probably all of you in this audience are aware of, are made out of atomic nuclei and electrons held together by electromagnetic forces, and so essentially by photons. And this was broadly understood thanks in large part to Niels Bohr in the early part of the 20th century, and refined in later developments in quantum theory. But it left the big question of what about those nuclei? Those nuclei contain all of the positive charge and almost all of the mass of atoms in a very, very small little bundle at the beginning, at the center. As people started to try to understand the properties of nuclei, a very big step was to have a model of nuclei according to which they're built up of more basic particles called protons and neutrons. In our modern understanding, protons and neutrons are very, very closely related, and we use a common word, nucleons, for them, things that make up nuclei. Oops. And then the last step was understanding that nucleons in turn, that is protons and neutrons, are made out of more basic objects, quarks and gluons. As far as we can tell, the electrons, photons, quarks, and gluons are truly elementary particles. What do we mean by that? Well, they obey simple and beautiful equations, so they don't give any sign of being complicated objects that are made out of smaller things. Also, electrons and quarks have very similar properties, and photons and gluons have very similar properties. So these are elementary particles that, as far as we can tell, are governed by simple, beautiful equations. In fact, I would go so far as to say that they're defined by the equations they satisfy. So if you want to understand what an electron is, if you ask a physicist what an electron is, you can get a lot of talk, but ultimately an electron is a thing that obeys the equations of electrons. And similarly, a photon is a thing that obeys the equations of photons. in those equations, you have to insert very, very few kind of abstract properties. So electrons have spin, they have electric charge, and that's basically it. Photons have very specific interactions, which I'll talk about momentarily, that respond to charge, respond to electric charge. And the overall theory is called quantum electrodynamics, or QED. This is one of my favorite quotations from Heinrich Hertz. Heinrich Hertz was an experimentalist who thrived in the late 19th century and whose greatest achievement was to show that the equations proposed by Maxwell about 30 years earlier for electric and magnetic phenomena in fact governed reality. In the process of doing that, he invented the technologies that became modern radio and ultimately all forms of electronic communication. So here's what he said, and I'm just going to read it, even though you could read it yourselves, because, well, I get a kick out of reading it every single time. So one cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them. And that's certainly true of Maxwell's equations. One of the reasons one can say that these equations are beautiful is that they have not only dry equations, but they can be expressed without loss of information in terms of pictures and geometry. So these are Maxwell's equations. One of them tells you how, this one here, it tells you how the so-called flux of electric field is governed by charges. And I won't attempt to do the definitions very precisely, but you can see electric fields coming out of a charge and the exact way in which they do that is the content of Maxwell's equations. And there's a similar equation for magnetic flux, but there's no magnetic charges, so you just get as much coming in as goes out of any closed surface. And then you have that magnetic fields are caused by circulating magnetic fields are caused by currents, electric currents. This was the great discovery of Ørsted. And then two equations that link electric and magnetic behavior. One says that circulating electric fields are generated by magnetic fields that change in time. And then the thing that Maxwell himself introduced, the effect theoretically to make the equations balanced. So the others were extracted from experiments. This was added on the basis of symmetry and balance of the equations, where you have changing electric fields produce circulating magnetic fields. And that's it. Those are the equations, and they can be written down, as I said, without loss of content in a really honest way, just in terms of these pictures. So that's why Hertz said they're very beautiful, and you get, and it turns out, as he showed, that you get much more out than put in. So the whole phenomena of radio waves, the explanation that light is a form of electromagnetic phenomena, all of those emerged from the Maxwell's equations, although that's what wasn't the initial motivation. Quarks and gluons obey even nicer equations. They kind of have Maxwell's equations on steroids, whereas in electromagnetism, there's one kind of charge, electric charge. In the theory of quarks and gluons, you have three kinds of charge that are often called color charges. That's why it's quantum chromodynamics. But really, they have nothing to do with physical color whatsoever. This is just a colorful way of referring to the fact that you have three different kinds of charge. And gluons are, as I said, very similar to photons. Gluons respond to these charges and
still a little bit of a problem with the back. If you can speak a little bit higher.
Sure, I can shout for a while at least. Okay, and we can make a similar statement that quarks and gluons are governed and defined really by a beautiful theory called quantum chromodynamics, or QCD. And it was by looking for symmetry and beauty in the equations that we were led to predict the existence of gluons and all the properties that they have. So they are really, I like to say, they're the avatars of symmetry. They are embodiments of theoretical ideas. Quantum chromodynamics, or QCD, you can write down the equations fairly simply, but solving them is another matter because it's a quantum theory. The quantum part of quantum chromodynamics is very, very serious. Fluctuations in the fields have to be taken into account, quantum fluctuations. This is what our eyes would see if they were capable of resolving distances very, very tiny, below 10 to the minus 14 centimeters, and very, very fast, 10 to the minus 24 centimeters. Our equations tell us that the gluon fields, which is what you see here, would be fluctuating. So they'd have regions of high intensity indicated by red and lower intensity by the softer colors. This has a repetitive loop, but in reality, it doesn't repeat. And the properties of quarks are very much conditioned by the fact that they have to propagate through these fluctuating fields. That's what leads to the characteristic behavior of protons and neutrons and all the things we calculate in quantum chromodynamics. We can have quite a bit of faith that this picture is accurate because the same calculations that go into making this picture go into making many, many successful predictions of things we actually do observe, such as the masses of many, many particles made out of quarks and gluons. As I said, quarks and gluons are similar, very similar, to electrons and photons, respectively. And out of electrons and photons, plus nuclei, you can make atoms. The analog for quarks and gluons are so-called hadrons, and like atoms, they can exist in many different patterns. And these are called hadrons. They're protons and neutrons are one example, but there are a whole bunch of other examples that go with funny names like pi meson, k meson, rho meson, k star, eta, and so on down the line. And they all have different energies, which then, according to E equals mc squared, means they have different masses. They have different amounts of energy locked up in them. That is the motion of quarks and gluons. Quarks and gluons themselves are almost massless. So this is the origin of mass. And it works. You can see that this theory accurately calculates the masses of all those particles. And one of them, N, is that nucleon I was telling you about before. And so this gives you an explanation of the origin of mass, the origin of most of our mass, the origin of mass of protons and neutrons based on pure energy. The quarks and gluons have essentially zero mass, but inside a proton, they're rattling around, moving around, and so they have energy. And now, if you use Einstein's famous equation E equals mc squared the other way around to say m equals E divided by c squared. When you have all this energy concentrated in an object that's overall at rest, its mass is the energy inside divided by c squared. And that's why you weigh what you do. So if you're overweight, need to go on a diet, you can blame QCD for that. Okay. Quarks and gluons are famous for being shy, or we say confined. That is, they've never been seen individually in isolation. There are strong forces that keep them, when you try to separate them very far, that keep them, that pull against that. However, if you look at reactions at very high energy, then quarks and gluons can separate for a brief amount of time. And once they do, they set in motion jets of particles, flows of energy and momentum, which you can see quite visually. And so by following these flows of energy and momentum and comparing them with the predicted initiating flows of quarks and gluons, you can literally see the quarks and gluons and compare calculations of how often they're supposed to be produced at different angles with different shares of energy. Sometimes you get two particles, that's a quark and an antiquark. Sometimes you get three, that's a quark, an antiquark, and a gluon. And you can test the theory in very great detail based on that kind of idea. And since this was already shown, I'll say that by doing things like that, many different kinds of experiments with different kinds of particles going into other kinds of particles, observing these jets, so-called jets coming out, and comparing with the theory, you can test the theory and also describe most of what goes on at accelerators quantitatively and in detail. So that's the glory of QCD. Now I'd like to not just dwell on the past, but talk about where we are today and frontiers of knowledge where QCD is being applied to new kinds of problems at the frontiers of current day science. It's very much a living subject. So first I'll discuss QCD at the frontier of precision and its application to something called the muon magnetic moment, which appeared in science news headlines 2 or 3 years ago, and is still, as you'll see, an unresolved question. So what is the muon magnetic moment? Well, first of all, what's a muon? A muon is a heavier version of an electron that particle physicists love because it's relatively easy to produce. Because it's more massive than an electron, it's sensitive to different kinds of effects that electrons, hypothetical effects that electrons are not so sensitive to, but also because it's convenient to study, because when it decays, it gives away which way its spin was pointing. So you can study how the spin it responds to different kinds of effects and how strong, for instance, its magnetic field is, how strongly it interacts with external magnetic field. So a muon is a particle that has so-called spin 1/2. It's always, you can think of it as always spinning. So like the Earth, it's rotating around. And like the Earth, there's a magnetic field that comes out of the fact that you have a spinning object that's electrically charged. And since the muon is an elementary particle, we can predict precisely the magnitude of the magnetic field associated with its spin in principle. As I said, muons are convenient to study, and people make very precise studies of them. But to make very precise studies, you have to have precise instruments. And to make lots of muons, you have to have accelerators that are capable of producing muons. And years of development went into making instruments that were powerful enough to do extremely accurate measurements. Physicists are fanatical about making accurate measurements, as you'll see. And this work was originally done at Brookhaven National Laboratory, but then people realized that they could make use of more powerful beams at Fermilab National Laboratory, which is unfortunately very far away. So they had, rather than trying to reproduce the hard work that went into making the accelerator and instrument that was ideal for measuring this magnetic moment, the amount of magnetic field that a spin produces, they just moved the whole darn thing over, floated it up the Mississippi River, and did the last bit on a truck. Yeah, there you see. This is the legendary big move. Why do people do that? The reason is that the reason it's worthwhile to make extremely accurate measurements of the muon magnetic moment is because it's something that theorists can also aspire to calculate very, very accurately. So you can have a confrontation of theory and experiment at extraordinary levels of quantitative precision. There's nothing really like it in any other part of science. But to do that, you have to to do it as accurately as the experiments can measure, you have to do rather elaborate calculations. I showed you a picture of those fluctuating fields. Those fluctuating fields that affect the motion of particles and affect the properties of muons, and to calculate the actual properties of muons, you have to take the beautiful basic equations and then see what the effect of all those fluctuations are to get the observable properties. And that involves calculations of things that look complicated and in reality are much more complicated than they look. Thousands of diagrams, each of which encodes complicated integrals, but people worked hard and did them all and got the calculations. The calculation, once you bring gluons in, however, the fluctuations get even, so those are fluctuations that involve photon fields, basically, and also pairs of electrons and muons. But you also have, when you try to do a really, really, really accurate calculation, you also have to bring in the possibility that the muon gets affected by those gluon fields whose fluctuations are much, although they're governed by QCD, governed by definite equations, are much more difficult to calculate. So that's a challenge. And when the theory and experiment were compared, they didn't quite agree, and so people thought there was something, or suspected that there was something wrong in the underlying theory. This is the a situation that was revealed when you compared theory and experiment. So one thing I'd like to call your attention to at the beginning is that we're looking at quantitative comparison of the magnetic moment, that is the amount of magnetic field produced by the spin, that's given by something called the G factor, or G minus 2 over 2 is something that's convenient, well, convenient or not, it's what they plotted in this graph. And this is being compared between theory and experiment at the level of 1 part in 10 to the 10th. So you do the calculations to 10 decimal places, and you do the measurement to 10 decimal places, And physicists get all upset if they don't agree. It's glorious. You don't find anything like that in chemistry or economics or and they don't agree if you calculate those gluon fluctuations in one way, and they do agree if you calculate those gluon fluctuations in another way. If you calculate the gluon fluctuations based on taking other experimental results and translating them over into input to the Muon G minus 2 calculation, you get this result. If you just do the calculation directly by putting the equations of QCD on a computer, experiment be damned, you just put it on a computer, then it agrees. So it's an unsettled situation. That's sometimes how science is. And we'll just have to work on doing better calculations and better experiments and see if the underlying theory has to be changed or not. So it has profound implications, I would say, maybe not for the history of the universe. It would have profound applications. It would mean we need to change our theories in ways that might affect the history of the universe or how we understand the Big Bang, conceivably. But to me, it has a profound implication, whatever happens, which is that we can get to accuracies of 1 part in 10 billion and demand of our theories that they still work. And if they don't work, we worry about it. So now I'd like to switch and talk about something that's in a way grander as a physical phenomenon or set of physical phenomena, but where precision is not necessarily so important. This is the application of QCD at the frontiers of astrophysics. And QCD is particularly important in understanding the astrophysics of extreme events when you have strong interactions, when you have many, many nucleons close together, and the interactions among them become important, and you ultimately have to analyze in terms of quarks and gluons. This occurs in supernova explosions, in neutron stars, and the field is now getting shaken up by observations in gravitational wave astronomy. So this is what happens to a star as it gets old and burns its fuel. Initially, the star is made almost entirely out of hydrogen and helium, but it derives its energy from the hydrogen combining by a series of reactions into helium and releasing energy. And then the helium combines into carbon, carbon combines into fusion. All of these occur in smaller and smaller shells as the star gets older. And ultimately, this comes to a close when you get to iron, because iron is the most favorable arrangement of protons and neutrons, of nucleons. And after that, you lose energy by trying to burn it. And when that happens, the star can no longer support itself by the thermal energy, the thermal agitation caused by the energy release, the burning of nuclei, and it starts to collapse gravitationally. This is a reconstruction of the history of a star that we actually got to see explode. This is supernova 1987A. It was born as something that weighed 18 times as much the mass. We can reconstruct the history with some confidence based on theoretical astrophysics. It was born about 11 billion years ago when humans, well, this is not right. This was well before ape men emerged, unless you have a very generous definition of ape men, or what kind of apes you call men. Okay, but never mind. Here, so it goes burning hydrogen, and so behaving like kind of a normal star, but such a heavy star burns its hydrogen faster than our sun, much faster, because the gravitational force that's pushing it together is stronger, and therefore you need higher temperatures and more burning in order to support it. And 700,000 years ago, the time that Homo erectus was emerging, the star exhausted its hydrogen, burned in different ways, including up to nitrogen, started to pulsate. This is a sign of incipient instability. Burned helium for a while, and then things got out of hand over here. When the helium is exhausted, then it starts to burn really, really fast. The nitrogen burning refers to up here, not where it's very misleading. And then carbon ignites, then nitrogen, and then it becomes a supernova. All of this is governed by QCD. All of those nuclear burning processes are strong interaction processes, except for the one that burns hydrogen into helium. That's a weak interaction process, which is why it's so slow. Because that one has to change protons into neutrons, it turns out, and that's a weak interaction process. Leaving aside the details, we can account for most of this brings in QCD and all of it to understand it properly. And then, boom, that's a supernova. And to understand the nature of the explosion and also what is left at the end is a great challenge, and we need to call on the equations of QCD to meet that challenge. The end result of supernova explosions could be roughly two things. One is a giant atom, a so-called white dwarf. This is where, it's a giant atom. So where the so-called Fermi statistics of electrons supports the white dwarf star against gravitational collapse. But that's another subject. I don't want to enter into that. The neutron star is the end result of heavier stars' evolution into supernova. And supernova, it's what gets left over. Probably is what's being left over in the case of supernova 1987A. In this case, it's a giant nucleus. It really is a giant nucleus held together by gravitational forces resisted by strong quantum mechanical forces. By the way, I should say that stars in general are, when they're burning, they are doing fusion reaction on a giant scale. That's what they are. They're giant fusion reactors. We'd like to make fusion reactors here on Earth. We've been borrowing on the great fusion reactor in the sky for most of our requirements since the dawn of biology. But without the gigantic gravitational fields necessary to hold this hot matter together, it's much more challenging. And that's why getting fusion to bring it down from the sky to here on Earth is a big challenge. Okay. Now, to physicists, neutron stars are a wonderfully ideal object. For QCD people, they are kind of the intellectual equivalent of black holes, but more interesting. Black holes are just this empty stuff. QCD has lots of matter that's strongly interacting and equations that are very rich and probably containing new phases of matter inside as you go deeper and deeper inside the neutron star. We'd like to understand the structure of neutron stars. Our equations in principle tell us what that is, but so far no one has been able to rise to the challenge of calculating the consequences of those equations to calculate the structure of neutron stars from first principles. Meanwhile, however, that's become an extremely timely problem because experimentalists, people studying gravitational waves in particular, are beginning to tell us what's inside neutron stars. When you have pairs of neutron stars that gradually spiral into each other and lose energy by radiation, eventually they merge, and when they merge, they get torn apart. At the same time, they emit gravitational waves, and the gravitational waves allow us, now that we can detect gravitational waves, to hone in on the part of the sky where neutron stars have collided. And also, the nature of the gravitational waves tells us something about the process, the last moments of when they collided, because that's violent motion that produces the gravitational waves. So we're getting much better data about neutron stars that reveals something about their interiors. And once you know the gravitational waves tells you where to point, you can also look and see the visible light. You can see radio waves. This is called multi-messenger astronomy. It's becoming a very, very vibrant, active field. And we don't know exactly what's going to emerge from all these studies, but let me show you one highlight that's already emerged. We've got, as a result of these multimedia, multi-window, multi-messenger studies of neutron star mergers, we've been able to make much more plausible, and even, I'd say, the consensus view now, more data would be welcome, the consensus view is emerging that most of the heavy elements you're familiar with actually originate in merging neutron star events. So when neutron stars merge, you get many, many neutrons in a small place that react with each other. The heavy parts of the periodic table, the elements beyond iron, which have more neutrons than protons, where did those neutrons come from? It's been a big puzzle in astrophysics where those come from. The normal burning of star doesn't give that, and just blowing it up in a supernova also doesn't really help. But if neutron stars merge, well, then you get lots of neutrons interacting with each other, and you can build up, when that fragments, from those fragments, neutron-rich elements. So it's now believed that all of the gold, or let's see, gold is AU, no, gold is AG. Gold and silver, almost all of it, is due to neutron star mergers. And you can see all of the polonium, all of these other things, bismuth, iridium, uranium, comes from neutron star mergers. Amazing. And of course, to really do justice and calculate how that works, we're going to have to use QCD very heavily. So finally, I'd like to discuss QCD. Oh, not finally. Let me discuss next. I'll discuss QCD at the frontier of extremeness, briefly. Oops. Matter at ultra-high densities and temperatures. This subject is studied at what are called relativistic heavy ion collision machines. There's a big, the LHC at CERN near Geneva is one of the places where these studies are made. But another one is Brookhaven National Lab, which is pictured here. It's a relatively smaller thing, but still pretty big, where you collide heavy nuclei, typically gold nuclei for some reason, at very high energies, make a small-scale version of colliding neutron stars, and that you can deal with and study what happens. This is what it looks like inside. You need to guide the particles that move so fast, to bend them at all. Well, first of all, you don't want to lose them once you've made them, because you put a lot of energy, work into making them move fast and have a lot of energy. You don't want to lose them, so you have to bend them around into a circle. And because they're moving fast, they don't want to be bent. But if you have strong magnetic fields and sort of coax them gradually into a large circle, you can just about make it work. So that's what goes on here. And these are extraordinary feats of engineering. See, all this stuff coming out is meant to make the magnets really cold so that they can be superconducting, so that the currents can circulate without dissipating a lot of energy. And yeah, it's extraordinary. And the beams have to be very, very precisely aimed at each other, because these are very small particles. To give them a chance to collide, you have to have beams that are very, very tight. And tremendous science. Well, here's something that's a little more familiar. When you have a material, say water, it can exist in different phases. Exist as a solid, ice. It can also exist as a gas, a liquid. And one of the remarkable things about water, it has a so-called critical point. As you go up in pressure, and the difference between the gas and the liquid phase, or go up in temperature and do both. The difference between the gas and the liquid phase gradually gets less and less, and at a critical point disappears altogether, so that you can pass continuously from gas into liquid with no dramatic change, no so-called release of latent heat. And this is explained in the science of thermodynamics and statistical mechanics, which is a profound development in physics and chemistry applied to the description of physical reality. Does that kind of reasoning work at scales that are roughly 1 billion times smaller? That's a question that we can ask. Do the same principles, the same physical principles, describe the kind of matter that exists at much greater density? And that's what you can study by, at these relativistic heavy ion collisions, you can very, very briefly produce high concentrations of, so-called baryon density. This is kind of basically the density of quarks. And temperature. These temperatures are in MeV, so 100 MeV corresponds roughly to 10 to the 13th degrees Kelvin. So these are really hot. Okay. Out here, theoretically, at very great density, you have the world's greatest high temperature superconductor. This might exist inside neutron stars. We don't know where this boundary is. That's one of the interesting questions that's going to emerge from future studies in multi-messenger astronomy. But here at these heavy ion collision machines, you can study this region of heat over here, especially at very high temperatures and relatively and high, but not that high quark density, and theoretically, we can use the same principles as we use on scales billions of times larger, the same kind of reasoning, same principles, to predict what's going to happen when you, and combined with the equations of QCD, to predict what's going to happen in this case. And one of the predictions that emerges is that similar to the critical point of water, where you have a continuous change, what was discontinuous before, the difference between water and its gas, steam, goes away, and you can get around it. Similarly here, the quarks and gluons, which don't exist as isolated particles normally at earthly conditions, gradually the difference between the liberated quarks and gluons at very high temperature and their confined version inside protons, neutrons, and the other strongly interacting particles, the hadrons, disappears at a critical point. And it would be very, very interesting to physicists to identify that critical point. And that would shed light on the early universe, where you basically move along this line of very high density, and also give us confidence that we can understand the diagram altogether, including those questions about neutron stars I mentioned. And I'm expecting, actually, in the next few months, that there will be announcements of progress on this question. The people have taken the data and are analyzing it now. And the rumors have leaked, as you see here, that this critical point in fact exists, and they've located it, and we can start to compare with the theoretical expectations that are also informing us about neutron stars and the early moments of the Big Bang. It's very nice to be able to check those predictions in controlled circumstances. Okay. Finally, let me talk about QCD at one more frontier, the frontier of intellectual adventure. As I mentioned, QCD is very similar in its basic structure to quantum electrodynamics. It's like quantum electrodynamics on steroids. The weak interaction, it turns out, is also governed by a theory that's a lot like quantum electrodynamics, fundamentally. There are various complications, but if you strip away the complications, the strong, weak, and electromagnetic interactions, although their manifestations in the physical world are extremely different, turn out to be related by very, very similar equations according to modern understanding. It's just that in the strong interaction you have 3 different kinds of charge, in the weak interactions you have 2, and the electromagnetic interactions just 1. And the strength of those interactions are also different. However, the calculations that go into asymptotic freedom that tell you that the forces between quarks get weaker when you go to short distances can also be applied to those other interactions, because they have very similar equations, do the same sorts of calculations, and you can see what happens. And when you do that, you find that they all become equal when you extrapolate down to very short distances. And if you pursue it further, you find that gravity, which starts out much, much weaker than the other forces, I mean much, much, much weaker, actually gets severely modified as you go to shorter and shorter distances, much more severely modified in strength, and they all come together at more or less the same point. So this is a very strong inspiration to think that there's an underlying theory that we almost have that can bring them all together. Now I'd like to show you a hole in our understanding of QCD. QCD allows an interaction that doesn't happen. This is really irritating to physicists. So QCD allows an interaction, which I've written in very indecipherable hieroglyphics here, I'm sorry, but this is an interaction between gluons that is not observed. So QCD allows it. So the main interaction among gluons is what QCD describes, and accurately, but there's another possible interaction that doesn't occur. Or rather, experimentally, one finds that the natural measure of its strength overestimates its actual strength by about a factor, at least a factor of 10 billion. So that's rather unsatisfactory. Seems like quite a coincidence. Or is it? We can attempt to understand this peculiarity if we change the theory, expand the theory a little bit, so that number is actually something that has a life of its own. We make it into an object, instead of being just a number, we make it into an object more like the gluons, the photons, the quarks, and the electron that are described by entities, fields that change in time and can create and destroy these particles or make them move around and so forth. So we promote that number into a dynamical entity that has a life of its own. And this can be done in a quite simple and elegant way. And then we can take the theory thus constructed and run it through the Big Bang, see what happens to this field as the universe evolves. So here I've stepped back and represented the field as just one object. So this is a representative point, a representative value of the field, and we see how it evolves in time as the universe evolves. And if you set the theory upright, which is not artificial, you'll have to take my word for it. If you set the theory upright, it's very easy to have this field wind up having a value very, very close to zero. So that's what it wants to do. That's what it wants, where it wants to go. It's a kind of theory of evolution for what used to be a number, or a so-called coupling constant, now becomes a dynamical entity that wants to be zero. It is zero, but it also wants to be. So we say it is zero because it wants to be zero. Okay, so, and if you run the equations, it spirals down as the universe evolves to a value which is not exactly zero, but close enough to zero to be consistent with those experiments, less than a part in 10 billion. And the field that's involved is called the Axion. I named it after this laundry detergent because it cleans up a problem with an axial current. But really just because I thought this was a cool name for a part. Long before I had any specific particle in mind, I had the ambition to name a particle Axion because of this. And remarkably, this axion was introduced to solve a purely theoretical problem, almost an aesthetic problem. Why is that number so small? But it turns out that it has consequences that were highly unexpected to the inventors of the theory. I can attest to that. that turned out to be potentially a great gift to our understanding of the universe. This is an indication, one among many, that the universe contains a new kind of matter, something that cannot be any of the stuff that's in the so-called standard model in our current understanding. It doesn't have, none of the particles we know about has the right properties. But you see, when you look at that image, let me go back to it. It doesn't look like a normal image of the sky. It looks distorted. And in fact, you can see several copies of objects that look remarkably similar. And look at these. These look like a ring of galaxies that have been highly distorted. What is going on? Well, you can understand this kind of picture, and there are many of them by now, in the following way. When you're looking at a distant galaxy, or several objects that are behind a big agglomeration of mass, a cluster of galaxies, gravitation, according to the general theory of relativity or just common sense, gravity should gravitate and bend the trajectories of the particles. And if that happens, you can see that there's more than one path for a light ray from this galaxy to get to the telescopes on Earth. Okay? So you see several different images at different places. Okay? When you reconstruct this image, you would say that, oh, you just extrapolate this line, and you would see an image out here, like what kind of a copy of the galaxy, and another image out there, as well as the more or less straight image that comes through the middle. And that's a lovely explanation of the phenomena. That's qualitatively correct, but quantitatively doesn't quite work. You need about 6 times as much mass to do this job as you get when you add up all the mass of the stuff in the galaxies and the surrounding gas clouds that we can test, that we can observe, that astronomers know how to observe. This and several other kinds of observations that otherwise would be very mysterious get explained if you introduce the hypothesis that there's something called dark matter, a new kind of particle, made of a new kind of particle that contributes that extra gravity, but otherwise hardly interacts with ordinary matter at all. That's why astronomers haven't observed it. So that's the so-called dark matter. Axions are just right to make the dark matter, just right. It settles down, that field settles down to almost zero, but not quite. There are residual wiggles. Although they're numerically very small, the axion field theoretically is supposed to be very, very stiff. And so even small oscillations involve a lot of energy and can be translated into a fluid of axion particles surrounding us and making up the dark matter. And this picture works out very, very nicely when you work out the details and really would explain the astronomical observations. But is it true? Okay, that evidence is kind of thin, very speculative. Well, the theory predicts how that the axion, as I said, interacts very, very feebly with ordinary matter, but it does interact a little bit. And in particular, it interacts with electromagnetic fields or photons. And one thing that it can do is, in the presence of a magnetic field, convert into a kind of photon which the right kind of eye can observe. Okay, so this is a kind of design for an axion antenna, a kind of detector that would be capable of checking if this whole theoretical structure and appealing speculation in fact describes the world. And people are taking this very, very seriously. Here you can see the so-called IAXO instrument under construction, I believe, at CERN. You can see the scale. This is a rather tall Scandinavian physicist. And this is a gigantic instrument filled with magnetic field, filled with very strong magnetic field. You use magnetic, those guiding magnets. Remember, some of them were left over when the LHC ring was produced. And so you use them in here. And this, since the signal is very weak, you have to keep this thing pointed at the sun. And the idea is to see if the sun is emitting axions that can be converted into detectable photons. And this experiment probably won't work, but people want to try. People will, try. This is what will work, I think. We have a different design, a different kind of antenna that also needs a big magnet. And here's the kind of magnet that we hope to use. And the numbers, the estimates of the sensitivity of the instrument you can insert into this magnet, given the magnitude of the magnetic field it can produce and so forth, lead me to think that we have a good chance of detecting the axions if they in fact make the dark matter of the universe. So keep calm and watch this space. So here, as in each of the different frontiers that I've shown you, QCD is pointing the way to new scientific questions that I hope you agree are of tremendous interest. And so we're justified in recalling Heinrich Hertz again. One cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers. And I can tell you from experience that's definitely true. And that we get more out of them than was originally put into them. Thank you very much.